Hello, first of all. I'd like to thank you all for being here on Saturday morning, so early here, and first thing in the morning, and it's almost full. We have lots of people here with us. This paper I'm going to present with Alvaro, myself, and some friends concerns Bluetooth Low Energy, with which we've been working along the last year precisely. And we've been studying very interesting subjects, first of all, because this is a protocol and a technology which is part of our daily life. It's what you have every day. We have Bluetooth Low Energy everywhere. So it's interesting for security issues to assess the security of BLE, Bluetooth Low Energy devices. We wanted to talk about it to explain BLE technology, the environmental characteristics, news we've got on BLE technology, and let's show you some attacks. When we audit, we can use what we've learned about attacks, breach, security breach in the case of BLE. I am this guy on the picture. I was 7 years younger there. Well, I look almost the same. And this is Alvaro. Our dear friend, as Alberto said, he is working at the innovation lab of 11 Pack company. We're going to make a short introduction, theoretical introduction on Bluetooth Low Energy. Then we will see some news on BLE, what has happened regarding security issues. We're going to assess, we're going to present several attacks that already exist. We're going to give it a try, to do it directly online, and we're going to mention how to strengthen security. The interesting thing when we talk about BLE is what could I do to avoid attacks, to prevent attacks? How can I enhance the security of the devices, provided Huawei will allow me? Let's start with the introduction on Bluetooth Low Energy. Bluetooth Low Energy is a protocol, it's a wireless protocol. You all work with this in your daily life, and you all know BLE. It started with the need that cell phones, mobile devices could use Bluetooth systematically without high energy consumption. Low battery problems will be avoided. Here we have the 2.4 gigahertz frequency bandwidth, and we have here 1 megabit per second. And we have here the outcome. It is Bluetooth 5 since 2016 with better transfer rates. The distance is improved, and there are some other changes like algorithm for frequency hopping. We have here the release 4, release 5, and we wanted to present to you here what I've seen. It's a barrier, it's a problem of layers. When you have a stack, BLE stack, and the analogy here is the OSI reference model, you'll know, with the 7 layers, the physical layer, the link layer, the network, the transport layer, and so on. And we are going to see BLE stack here. We have a physical layer, we have a link layer, we have a control layer and logic layer, and we have several layers that are related with OSI. And how about BLE? BLE uses 40 channels, 40 radio frequencies, with we have 3 for announcement. It's for your BLE devices could tell you, we're here, we are here, we have services and profiles. We have 37, 38, and 39 for announcements. We have 37 data channels from 0 up to 36. Those are things we have to know. Then, how about it? How about frequency distribution? Every 2 megahertz we have a channel. And we have here, you see, it is not a logical order. First one is the announcement is 37, then 0, 1, 2, then we have 38 in the middle of this, in between, and then at the end 39. They are sort of spaced, but every 2 megahertz we have a frequency channel. More concepts. One important concept is the address axis. Axis address is significant. We have to use it. The master and slave will use this. The one we're connecting to and the one we're exchanging data with. So we have the axis address, which is generated by the master. It's randomized. And then there is an important detail. Two masters having the same address is very low. It's neglectable. It's complex, but this will exist, might exist. And we're going to talk about this when we will assess things. We will see all the concepts there, and that's part of the attack strategy. How does it work? Are we sending data on a channel? That's it, once I establish connection? No. Really what's happening is frequency hopping. We're sending data and we remain at a given channel during a certain period of time. How does it work? Well, we have a channel map here. When there is a BLE connection, we have a channel map. And those are channels both ends could use. We have channels we could get connected to send data. 40 channels, but the channel map will delete 3. Announcements are not available for us to send information. So we cannot have a frequency hopping into the 3 channels that are for announcements. The interval should be, the hop interval should be synchronized to the master and slave, and we see how often we're going to hop. So, and with the increment, we have a hop increment. That's the concept that's used for selecting the channel, the frequency I'm going to hop to. Then we have 2 algorithms. First one is this formula. It's a channel plus the leap mod 37. So it's a channel plus a hop increment. And that gives us a figure. We have then the 37 because I have to be from 0 up to 36. And then I'm going to hop from there. But I'm going to hop if the channel map tells me that I can hop into that frequency channel. If not, I have to calculate again, and I have to calculate and see if I can hop or not into the channel. Then an important thing is that in the channel map, and we're going to see this afterwards, let's keep this idea, bear this idea in mind. We're hopping, we have frequency hopping. It's a different frequency each given time interval. And how do we know that we're able to hop there? Because we've been told, thanks to the connection, they tell us, the master tells us that's a map and that those are the channels we could use. How will the master know the channels could be used? Because prior to the connection, the master starts changing, checking if there is noise or not. If there is a high frequent noise level, they won't use that. So they have 5 bytes per 8 bits. Each channel is represented. We have 40 ones, and it is represented as 0 or 1, if we could be using the channel or not. BLE packet has this appearance. On top you have the PDU, which is a protocol data unit, and we could encapsulate here 2 types of packets, the announcement and data. And in the case of announcements, we have the header where we could explain the type of announcements. We have a beacon saying we're here, hello, it's saying hello. We have the possibility of scanning. It's active scanning. This is the answer to the scanning. And I have the possibility also of showing the connection, saying we're going to initiate a connection. That's important. Important because we're going to use this mainly for the assessment. I have the codes here, you have the codes, and look at this. Capture up there is with BTLE jack, which is a tool we're going to use for certain actions and interventions, but when we capture this, we have a connection packet. We have connect request. One device has been connected through BLE to another one. You see the concept here, address. It's a session identifier of the connection, the hop interval, telling us here it's 24. 24 you have to multiply by 1.25. 1.25 is 30 milliseconds. We're going to remain there on the channel hop increment for the algorithm. For the hop algorithm, we're going to tell the opponent that is the value you're going to use for your algorithm with the 37 value mentioned before and the channel map. And this is represented here the way you see. And if we deployed the channel map variable, we would see that we have all the channels there, and 0 or 1 if it is possible to hop or not, or if it cannot be used. We have many devices, and perhaps your channel map could be reduced. It's different when you're alone. And here, Alvaro, you have the floor. Well, we've seen the first part of it, the theoretical aspects of the way it functions, the way the BLE theory works. And then we're going to see some news, some devices you might have at home, something that had happened and some failures. The first thing here is I want to introduce the wearables we have here. You have those devices at home, and you know that to work with those you need, from the wearables, you need to convey the information. And you have here the application, different types of wearables, so you wear the devices and we could exchange data. Here we're sending a notification, and this is a PK. It's an app, and they know how it works, and you can exchange messages. This is not the official app. This is application been developed for that purpose. We see now the notification has been conveyed, and we get it on the phone. This should happen only through the application, the application that's own, proprietary. How about it? It's this one that has compatibility with all the devices. We could outline PB, the ones you can read here. And as I said, this is an open source application. In Java, you can see the way protocols works, and it is Android 4.4 on. If we see the project, we have among the main, we have two types of characteristics, MIBAB, and we have the types of exchanges you could have. If we could accept, reject calls, you could set general information. We can have here a table where you see what's possible, what could be done with each of the devices. On top of this, this is the one of the wearable stars. It's the MI band 4. We have the Python library, and it is interesting that there are characteristics that could be used without authentication, and for other characteristics you need the key that's generated by the manufacturer's application. If we wanted to extract the key, we would need rooted the Android phone. What could be done without authentication? We can send alerts, we can set requests, we can send requests in order to obtain the, for instance, we have here the calorie consumption, the energy we need for that authentication, but there are very many things you could obtain without authentication, without any sort of key, authentication key. Vulnerability, those are the trackers. Trackers are the ones you could have to find your cell phone, to find your keys, and those are vulnerability in the tracker. Our Bravo is the one you see here, the iTrack Easy, and the ZZ Tech Not. Rapid 7 people found this, the creators of Metasploit. And vulnerabilities found is there are problems of ID tracker exposure, no authentication based on the cloud, and as they communicate with the servers, vulnerability might be there, like it is the case of the password. We will see a snapshot, and when you are making a call, you have the password they're sharing, and it is something that is shared by Bluetooth, and that's sending information to the servers and the panels, and you have the ID. That was back in 2016. You see here the devices, the trackers, and you see here the type of vulnerability in each case. That's part of Rapid 7. They discovered this. So it's available. We have here the blue dot, the cameras, the 360 fly cameras. When they wanted to configure the access point to get connected to the camera and to use it using Wi-Fi, the configuration of this app was done through BLE and was conveyed directly, was open. If we wanted to see the password of the access point, then it would be easy to get connected to the camera. Of course, you have to know the way it works, the way the access point works. How could we do this? Once connected, we can stop, we can start the video, have streaming, take pictures, vulnerabilities there. You have full vulnerability. In BLE, you could just have a flat transmission of the password. And here, mobility, electric mobility. In this case, we have the scooter, the M365. I don't know if you know the electric scooter, hacked and remotely controlled. They say update your scooter if you want to avoid hackers. We had this back in 2017, sorry. And I'm going to present here the scooter. They could receive BLE packets, in this case to block the wheel. You see, when the light is red, the attacker targets a victim. The attacker will now remotely lock the scooter, so you cannot use the acceleration engine, but the wheel is blocked. So you could accelerate all of a sudden, or you could stop all of a sudden. Here it goes backwards, and that is the end of it. We are losing control of the scooter. It was totally blocked. The wheel was blocked. And that's what to use for avoiding people to steal your device, the scooter. What happens here? We have a repository and having a reversing protocol. Here we can see how they got the logic approach. They start from 55AA, and then you have amount of data. You see if the information comes from the scooter onto your mobile, from the mobile to your scooter, if it is a cell phone to the battery of the scooter, or vice versa. Look at this. It's just to turn on the LED, the light you have behind. It is on the scooter. And we have here things that are not yet completed, haven't been analyzed yet. We know it's been conveyed, but we say, I don't know. No say, I don't know. So look at the, here, it is 55A04-2013. What is here written? You can see it's to turn on the light, the LED. We haven't got the application of the scooter. We're receiving the code, we're writing the code. We've seen when we have reversed the protocol from this open source, and we've written here we want to turn on the light, the LED, and we're going to send this to the scooter, and the lights will be turned on. Yeah, you see, it's been completely written, and that's it. Let's send it. We have here the scooter, and the light's on. Look, LED is on. No problem. That's it. That's the way it works. That's why BLE works. We don't need to have a matching key, whatever. We just get connected and we start working with this. And recently, and that's quite recently seen publicly, mid-February, and it was reported, it's true, that back in 2019, that was reported. What was this? Swain Tooth, vulnerability family, 12 vulnerability, and most of them Texas Instruments, NXP, Cypress, and Dialog semiconductors, microchips, and so on. The failure was that what was implemented here, there was an implementation failure of the way the BLE was working at the level SLK. The manufacturers, Samsung or other manufacturers, were not to be blamed. It was the SDK, the way BLE was implemented at the level of the chip of BLE. What happened then? Crash. for communication. The communication stopped. Also, the deadlock. They could freeze the device and you should reset the whole thing to make it back to life. And there was a bypass of security. They need matching, but due to the overflow of the key, we could overcome this, and it was not necessary to have any matching to get connected to a device and to retrieve things that required security protection and matching controls. We have here, in spite of the fact that it's 2020 news, it was seen back in 2019. This is why we have the date here, 2019. We have the devices concerned. When we talk about real devices here, the Band 3, NCC, Samsung, Galaxy Seed, we have here the wireless mouse, Amoeba, even though it comes from another manufacturer. So it goes on to another manufacturer's reference. We have medical devices for measuring glucose. It was the same. There was a crash. It stopped working. To see the video here, we have this lock. It's an intelligent lock. Same problem. They are always, as we see here, restarting. In the video, we see just that we haven't got access to the lock. We haven't got access to the lock. There is a bip, 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 bip all the time. And we see here that the University of Singapore had this, and they've seen vulnerabilities there. We could have an exploit, and we could see the code has been breaching security because the lock is not working properly. Then the assessment now. Well, let's move on to the assessment. And attackers, we are going to see different types of attacks according to this technology. First of all, sniffing. As it is a wireless technology, the way is air. So it's just, if we have here devices to see the air interface, it's like Wi-Fi. So in Wi-Fi, we always have, almost always, we have networks that are ciphered with protection and so on. Inside protocols, HTTPS, this is ciphered. But in the case of BLE, not yet. It's not yet been developed, not been disseminated. So we have many cases where the ciphering doesn't exist. No ciphering from the technology, and no ciphering, well, it does exist, but it's not been configured. And the profiles and all data circulating as part of the communication are not ciphered. We see that almost everywhere. So if we listen to what happens, what's close, we could sniff, we could see, we could catch data that are interesting. We have to see here replay, hijacking applied, hijacking in many fields, but applied to BLE. Jamming also, of course, this is another type of attack. But in BLE, you could also have jamming. The MITM, ciphering attacks also. This is going to be our demonstration. And the flat text, passwords, or when you send information also, problems. And then we will see applications that are hard-coded, and it's interesting. So sniffing we have here. It is just listening the air interface. There is no cable protecting us, so the air interface is free. So we're just listening to see what we can catch. And we have to know what goes on the air interface. There are 3 channels, so announcements there. We have to listen to the announcements to get a connection. Once you detect the connection, we're going to follow the connection because what? Because of what? Because we get the channel map, we're going to get the access address, we're going to get also the hub increment, hub intervals, all the data, all the parameters I've mentioned before, and we're going to be able to know this because they are not protected. So we see the configuration of the communication, and then we're going to use BTLE jack, and the hardware to be used should be, in principle, the ideal thing is to have the capacity of covering the 3 channels, or what we've done is to use a plate, And I'm going to show you this with a camera. It's a little plate, just a tiny plate, and this has been given to us by BBC. Yes, BBC, yes. And, well, you know, it's up to Microsoft. This plate will allow us, it's done for programming, it's for children. But with this application BTL Jack, we change it, and it's not for children anymore. That's going for us to listen to channel 37, for instance. And with other ones we have here, we're going to get connected to channel 38. We're going to listen to channel 38, 39. And we're going to put each plate to listen to a channel, and we're going to guarantee for sure that we're going to catch the connection among two different BLE devices.
Okay, a replay attack. Even if the drawing of the attack is done on a car obviously is not locked with a BLE device. I don't know if there's a model using this, but in principle there is no model using this lock. But you can understand how replay attacks happen. So we have a listening device when the person arrives trying to open the car, which is not the ideal scenario, but they use a command for the action. So we capture the frame, and then we can use it. We can use this frame, and the result is going to be the same as the result obtained by the user. So here you have some tools: BTCap, BetterCap, Gatool, NRF, Connect, which is mobile, developed by us at Telefonica, which is open source. So many tools to do that. Now, hijacking attack. Most of you know session hijacking, DLL hijacking, PLT hijacking, privilege escalation, but you can also hijack a session. So imagine you're using the original application of the scooter, for example, and we are connected, and all of a sudden, with one of these plates and with an application that has been set up, we can send timeouts to cause communication with the scooter is lost. So we can use the access address we know and establish communication with the scooter as if we were the original application. We have a video to show you this. And the first thing I would like you to see is look at the attributes. We have the connection, access address, increment, interval, channels, etc. So with this information, with the access address, we run a BTLE jack with the -T option, which is set up so that timeout is possible, but also we can connect to the scooter and being able to extract the features and the hijacking session thanks to the access address. So see how it works. We can use channels and send channels. So we have the farm here of microbits. So determining this and sending this is faster because we have the parameter, but as you can see, it takes long, probably 2 minutes to launch an attack. We try to get the interval then, and at this point, we have the hijacking attack. So the original application is not connected, and we can connect to the scooter. So what can we do? We can read the features offered by the device. For example, we have here all the features, the characteristics with the permissions, whether or not we cannot write or read, ID, and we can also write here. If we know previously, if we read the document, we could go directly and write the concrete characteristic on the concrete hijacking and send a parameter or a value. And we can write here and turn on the light of the scooter or turn it off. So in the case of vulnerability, we could block the engine. So so that when the user wants to start the engine, he will not be able to do that. And lastly, jamming. Jamming is oriented to another kind of technology. It's an inhibition. You can see that on the drawing very clearly. In the case of BLE, so this is like half jamming. So I send the timeout. I'm obliged your connection to be lost, but we're not avoiding the first connection. So it's half a jamming, actually, because when you connect after a while, you will not be able to carry out the operation. So Alvaro, I give you the floor to continue. Let's talk about MITM, man in the middle. But how does it work BLE oriented? Because it doesn't work the same way. So first drawing, using MITM for payment using Bluetooth. So how does it work? What you have to do is when a device is being announced that we want to do might in the middle, we connect to the device to know the services, their characteristics, and how they send ADV packets to connect. So the device, we can use the device to get the information. So when they connect to a false point, we redirect traffic. It's as simple as that. So GATAC and BTLE juice are the applications that do this. They are good to develop this concept I just mentioned. Ciphering. Pablo mentioned sniffing, but the sniffing can be ciphered. So what we have to do to access ciphering attacks is when the PIN is identified. So if we know exactly when the TK is sent temporary key, we can launch brute force to get the information with the keys STK, LTK. This is used to cipher the rest of communication. All the communication is done with this STK or LTK. What are the tools that we use to crackle captures that are ciphered? Well, precisely, crackle. For ciphering, when we capture, we need to have this framework, this list of packets. 2P unfilled, 2 peri-random, and LLL crispos, and LL start in request. So this is the data list that is necessary to carry out a ciphered communication. When the connection happens, this exchange of packets happens, and you can exchange data in a ciphered way. Then flat text password. So a request is done, so it's not the BLE protocol, but it's a device using BLE that requires internet for functioning. So the failure is that requests are a flat text or base 64. So we reverse it and we get the password that is encoded to manage the device. Then non-obfuscated apps. So this has always happened. Probably our code has things we don't want to share. So we see there's an application here. It's a smart lock actually with BLE, and you have the key and the coded password is hard-coded in the code. So let's see the BLE demo with Crackle. So we will conduct sniffing in a device we generated. So it's no a real device that is going to be harmed. So we faked, we simulated, we created locking. So using this microbat plate, we programmed through the framework of the shape of it using Windows with a very simple software, and we put the code. So now is the time for you to send Alvaro messages, because you will see them on the screen. So we're trying to connect to Wi-Fi. So let's do this. Okay. So the first thing is we are going to hear and listen to this, and we are going to say everything is going to be saved with website pi through a pipe, and this is going to be saved in a capture. To do that, okay, it's routed, pick up. Okay, now I got the pipe ready here, white arc, and we have here 2 microbits with 3 was enough for the 3 channels, but we have 2, which is 100% sure we're gonna get the packet. So it's paired already, I think. Okay, there you are. So it's really tense when you have when you get live demos, right? So the package, the connection package is there. The parameters we mentioned before. The channel map is very well populated. Okay. So now pairing. We are going to set up the microbyte for pairing. So 403. And we must trust what Alvaro is doing now. 830. Okay, here we are. So pairing has been done. White arc. On white arc, we'll see that all the packages are there, and sniffing is going to be running. So when he connects to the lock. So let's see that. Let's see the image. Okay, there you go. There you have the video. Smart log, a lock that is closed, a router lock that is closed, that is locked. So we simulate. We have an application. So we work with smart lock. We connect to. We connect and we send the code to open the lock. Okay, we had this copied, so copy paste. We send it, and now the lock is unlocked. So you can see the router lock is open, unlocked. That's it. So that is the capture. So see the attack surface is important, and we should be there for pairing, otherwise we will not be able to break coding. So it's 6 packages. You can see them ciphered or coded. We have a little above on the list the pairing part, and we are going to use now a tool called Crackled that Alvaro mentioned before, and this tool uses 2 techniques. It can use a cracking technique that is slow, so probably half an hour, 25 minutes if you try it. Well, it depends on many things, but it's a slow technique. But if we get this, see how the number we mentioned before shows up here again, and thanks to tilde K, we can use you can use it. We are gonna call it rooted decrypt. What's arc? So the framework, 156 packages. There's no possibility here to see the data, but in this case, it's like that. So, for example, 154. Apart from TCAP, we have the reboot protocol, and we can see here the code of the application. Let's see it. Okay, here you are on the screen, the code. You can see the code down here. Okay. We have broken the encoding, and we have obtained the command with a replay. We can replicate it with the replay, so we know the command to open the lock. Let's continue and finish the presentation, actually. So we have a backup, right, with the video, by the way, if you are interested. Then fortifying. Fortifying, you have to, the takeaways from this is, I'm going to use BLE devices, but you need to use secure channel. I'm not talking about frequencies, but you need to encode communication. And ciphering communication might mean using encoding elements that are not a 6-digit PIN, because this could be attacked, because the pairing can be caught, but it's better if you use other exchange of passwords mechanism, for example, ECDH, which is a little bit more robust, or using your own encoding if the device allows this enables this, in order to send our own encoded information, because this is going to be better. And also packaging signature, which is interesting because we can sign and manipulate packagings on the fly. Conclusions. So Alvaro, come here, come closer for you to be on the screen with me. So hacking BLE can be done by anybody. It's there for you to use this technology. And it's important to know attack techniques, because with the cell phone, the application used by Alvaro, NFR Connect, allows you to connect to devices with no pairing needed, and you can read, or you can use the FU mode, and the harm is going to be higher. Many manufacturers use encoded protocols. And then that's it. Thank you very much for your attention. And if you have questions now, feel free to ask. Thank you, Pablo, and thank you, Alvaro. Questions from the audience? Yep, someone has a question here. Good morning. Thank you for your presentation. It was very interesting. Let me ask you a question. Can you force to do pairing again so you can sniff it and crackle it? Well, if you insist, and if you jam up until the victim knows the device works bad, you insist on that, and of course you can do that. Are you talking about a device that is communicating to another one with a confidence that has been generating? Can we force devices to lose confidence? No, what I mean is, I don't love you anymore. Like that, something like that. I understand. I never tried. I thought about it, but I never tried it, so I don't know exactly if it might happen or not. But if I access the device, I'm not sure. Can we replace a Bluetooth device? We try to do that to see how they respond, but the confidence should be broken. But I'm not sure how to do that. Probably Raúl, if he's here, he can help us. Any other question from the audience? No more questions? Okay. Yeah, in the middle of the room, someone wanted to ask you. something. Good morning. I wanted to ask you if you could come up with a list of all the devices that might use BLE. I mean, uncommon devices. 1 month before the presentation, Alvaro and I were talking and said, let's create a list of devices and the list of types of devices. This list exists. Some people classified devices, but we came to the realization that, yeah, we know all the devices, which is good information, but we couldn't evaluate and assess and say, these are the devices, these are the hacks, and how can we match them to come up with consistent data. So types of devices were not included, but the list exists. I can tell you where you can find the list and the classification and with all the kind of devices. No, I was talking about a washing machine rather, or a toaster, why not? Yes, BLE is found everywhere nowadays, and if we look at Chinese devices, for example, you can find everything there. You can, now it's going to take longer, but you can buy a device in China with a BLE, and security in China is practically non-existent. Pablo and Alvaro, thank you very much for your presentation and for sharing your job with us. Please give it up for them.